Hi, Sherry.
Hi, Sherry.
Hi, Sherry.
Sorry to hear you're sick, but hey, hopefully this will help you out some. We've got 4.2, day 2. Real quickly, just to review, we said if you have a homogeneous differential equation, if you've got an nth order, that means there are n derivatives in that differential equation. If it's set equal to 0, you expect n linearly independent solutions. And that's what we used yesterday with the Wronskian to show that we had linearly independent solutions, as long as your Wronskian determinant is not 0. You could then say a general solution to the homogeneous equation would be constants multiplied to each of those n solutions. And that would be a wonderful general solution. Well, then what? We were venturing off to say, now, wait just a moment, we might not have a homogeneous equation. We could have perhaps the right-hand side being equal to f of x, not equal to 0. And once again, we could see that our general homogeneous solution is still used in a general solution. It's just that you have a particular solution that would solve the non-homogeneous. And we talked about that briefly. We're not even going to dive into that as much today, but I just want to keep reinforcing that. If you were to have y sub c plugged into this differential equation, of course, that would yield 0 if you were to substitute y sub c in there. You add y sub p into it, we would say, hey, if you plug y sub p in, that left-hand side would be f of x. So that's why that would work. That's why that would be true. Well, what's the big picture for today? The big picture for today, and this is really separating it at this point, we're going to say, let's just say that you know one solution for a homogeneous differential equation. We're going back to homogeneous. If you know that you've got one solution, you can find another one. And in fact, dare I say, I think I wanted to put my bar over here. So this is what we're doing today. Let's say you know one solution, you can find another. Now, we said that our solutions should be linearly independent. That means that when I divide y by y sub 1, I should get u of x, where u of x is not a constant. This is just another way, guys, a simpler way of saying that y and y sub 1 are linearly independent. We're saying that they are not constants of one another. So, what we're going to do is take y equals some function u of x times y sub 1. We'll substitute this into our differential equation. We'll do a power reduction like we did in chapter 2, and then we'll solve and eventually find our answer. So right now, this is the big picture. Let's quickly take a look at what this whole process entails. Again, everything today is homogeneous. Everything we're going to be talking about, you'll have a right-hand side of that equation is 0. And what I'd like to point out is they will always give you one solution at this point, at least. They'll say, let's just say you know that e to the x works. It makes that differential equation true. We're going to make a bold claim and say we'd expect a second answer that would be linearly independent. So that when I divide y and e to the x, I would get u of x. I wouldn't get a constant. I'd get something like that. Well, by the way, we could probably just write y equals u e to the x. I think that's the smarter way to do it, just for brevity. Help me out by finding a derivative. What's y prime? We've got to use a product rule, don't we? What would we get? U e to the x plus e to the x times u prime. You'd say, oh, would you look at that?
Well, wait a minute. We're going to need a second derivative. Get to say why. Well, look at the differential equation. It's second order. It's a second derivative. We have to go a little bit further. Here's the beauty of it. This is the cool part. Get a load of this. You're going to take the derivative of u e to the x. You just did that. You see what I'm getting at? You just took the derivative of u e to the x in that last step. It was all of this. Now I'm going to go one step further and take my derivative of u prime e to the x. Well, if I take my derivative of u prime e to the x, we need a product rule. So let's see, what would we get? U prime e to the x plus u double prime e to the x. Or e to the x u double prime. Is that making sense? Okay, well, let's combine it. You might say, what do you mean? Oh, like terms, I mean. Combine our like terms. Here's a 2 u prime e to the x plus u double prime e to the x. Well, here's where we're going. We've got y double prime minus y equals 0. Let's substitute everything we just found in there and see what we get. Y double prime is going to be this very lengthy expression we just found. And then you'd say, well, now I'm going to say minus y. What did we call y? It was just u e to the x. Now, at first glance, this might look a little intimidating. But you're like, oh my gosh, wow, look at that. Some good news, though. Something wonderful is about to happen. You're going to get a little canceling. Look at that. And we could reorder this. We could rewrite this. U double prime e to the x plus 2 u prime e to the x equals 0. Writing my higher order derivative first. And yes, this is homogeneous. I'm not used to seeing an e to the x out in front. Guess what I could do to both sides, though? I could divide. I could divide everything by e to the x. Wow. What do we get? U double prime plus 2 u prime equals 0. And guys, this is a problem that you did in chapter 2. You dealt with the reduction of order. So we could momentarily do one of these. We could say, well, let's let w, or whatever variable you'd like, be u prime. And then what would u double prime be? It would be w prime. Wow. The advantage to doing this reduction of order is now you look at the new differential equation, and we could even solve this with an integrating factor, couldn't we? We'd say, let's find an integrating factor and maybe make this a little bit nicer. So integrating factor would be e integral to the 2x and, no, 2dx, forgive me. What would that become? E to the 2x. So tell you what, I'm going to multiply everything by e to the 2x. Tell you what, I'll move the 2 out in front. Yikes, what was that? Okay, so you've got 0 on the right side. Would you agree with me, guys, that really on the left side I've got a product rule? You always do. Got that. And wow, right now we are so close to wrapping up. Hopefully you look at that, you could say, couldn't I just integrate both sides? Integrate the left side, integrate the right side? Yep, certainly could. Hey, what's the integral of 0? A constant, you got it. And over here we've got e to the 2x times w. And we're getting closer by the moment. How about I divide both sides by e to the 2x? And when I do that, how about I bring this back up over here? We'd say w is equal to c1, or I could even multiply both sides by e to the negative 2x. Either way you want to do it, it's fine. Divide both sides by e to the 2x, you get c over e to the 2x. You could bring it back up. It's all good. But what was w? W is really u prime. So I've got u prime equals c1 e to the negative 2x. Wow, we are so close to finding u. Guess what u is? I've got to do one more antiderivative. What's the antiderivative of e to the negative 2x? Negative 1/2 e to the negative 2x. Reverse that chain rule. Divide by negative 2. And don't forget, now you've got another constant. Wow. Wow. So that's what your u is in general. It's a two-parameter family. You could come up with two different arbitrary constants to work it out. What the authors suggest that we do at the moment is to choose the nicest, simplest forms of an answer that we could, because we want to find a very simple alternate answer, even with the simplest coefficients. Guess what I'm going to choose for C2, because C2 could be billions and billions of numbers. I'm going to let C2 be 0. And I'm going to let C1 equal negative 2. Well, kids might say, why are you doing that? Well, A, I'm going to get rid of the negative with that C1. And then I'm also going to cancel out the 2's. Now, if that's the case, we would have this as a possible answer. Guess what our u would really equal then? U would equal e to the negative 2x. In other words, have those constants chosen so that really we just have the most simple form of a function with no coefficient whatsoever involved. Now, immediately kids can say, well, couldn't you have billions of other answers? Yeah, of course, but we're just keeping it in general. Now, what did we start our assumption with? We assumed at the very top, look what was happening, that y was equal to u times e to the x. That would mean u equals e to the negative 2x times e to the x. What would our other answer have to be then? E to the negative x. That would be another solution. You could double check that it works. You could double check that it works, guys. You could very quickly say, well, what's the first derivative here? We'll just do this super quickly. What's the first derivative of this thing? Wouldn't it be negative e to the negative x? What's a second derivative? E to the negative x. Is it true that y double prime minus y equals 0? If I plug in the second derivative minus the original function, do I get 0? Oh, you bet. You bet we do. So that's all they're asking you to do right now. But if I were to go to a general solution, the general solution would be y equals c e to the x, c1, and then we could say c2 e to the negative x. Assuming that these are linearly independent, just by the way we set up that y was equal to u times the other y solution, that's more or less showing that they're linearly independent. You wouldn't even need to use the Wronskian on it, you know. Does that make sense? That's what we're doing for today. And it looks like